Wow. What in the world was that? It's been one of those supersonic jets. I heard the military was working on those things again. Sonic booms and the Doppler effect. Why do we have to go supersonic anyways, eh? I mean, you know what I mean when I say that, right? Supersonic? Doppler effect, you know all that? Right? No? Who am I kidding? You're not even really here, you're just a person in my head. I'm not crazy, don't look at me like that. I see you, I am blind. Yeah, I got the time. I'll explain it to you, kiddo. I have the time? I do have the time. So let's start off with sound. Sound is the vibration of air molecules. So let's say that the source of the sound is my hand, and right next to it there's the air. So that as the sound, to create sound, this object has to move back and forth, and that moves air molecules, which then hit the air molecules next to them, and then next to them, and then next to them, and then that happens hundreds, thousands, millions of times until it reaches your ear, at which point it stops, and your eardrum picks up. Your eardrum is just like a thin membrane of skin that's surrounded by hairs and nerves, and then those hairs and nerves pick it up, and then you can hear things. You got that? Yeah. Anyway, so sonic booms. Sonic booms are loud, explosion-like sounds that occur when an object of any kind reaches the sound barrier. So 771 miles an hour, give or take a few. Fun fact, while everybody thinks that there's only one sonic boom, there are actually two sonic booms. One at the very tip of the airplane, one at the very back, while the air snaps right back into place. Now this has been around since the dawn of time, since we've had an atmosphere, since we've had air. But the man who really put a face to this was Christian Doppler. He was an Austrian scientist, and he created the Doppler effect. Well, he didn't really create it. He just discovered it, and then he put a name. He put a name to it. So it's the reason for why waves act differently depending on the source of said waves and if it's moving or not. I was looking at a website the other day. What was it? It was physicsclassroom.com. Yeah, and so they had a great explanation for this. So I'm gonna try to explain it to you in the way they did it. So say there's a bug in the middle of a lake, a very calm lake or a pond, or a puddle, whatever you fancy. And so in the middle of that lake or pond, or I'm just gonna go with lake, there's a bug, and that bug is not moving. It's not moving at all, but it creates these tiny little vibrations with its legs or with its wings or with something, and that creates a ripple, and then that ripple is going to continue to get bigger and bigger and bigger, and so where you see the ripple, that's a wave. And so those waves are always going to stay the same. They're always going to stay the same distance apart, and they're always going to move at the same speed. They're always going to stay at the same frequency. So it's going to keep moving and keep moving until it hits the shore or the energy dissipates. But then, let's say now the bug is moving. So if the bug is moving, it doesn't matter which direction, if the bug is moving across said lake, and it is creating waves at the same time, you have something very, very different. The waves at the front, in front of the bug, are they're all bunched together. They're incredibly bunched together, and they're incredibly tight, and they're a very high frequency. Meanwhile, the waves behind this bug are much farther apart. It's so basically what happened was they took some distance they took some of the frequency from the front. They took it away. They took some of the distance from. They took some of the wavelength from the waves in front, and they moved it and they shoved it to the back. So you got very tight at the front, very loose at the back. And so that's the Doppler effect. It's why waves change depending on the source of these waves. And then when you reach the sound barrier, so like I said, 771 miles an hour, give or take, depending on where you are, everything changes. The waves in front, so the waves in the back, they all stay the same because they have all the room in the world to go and do whatever they're talking about. And so we're talking about sound waves here because we're in a plane, not in a bug. We forgot the bug. The bug doesn't go supersonic. Supersonic bug? What are you talking about? You're crazy. Completely crazy. And so the waves in the back, they're all fine, but they're still like a bit more stretched out than if they weren't moving, than if the source wasn't moving. But at the front of the plane, at the very tip, the sound waves have like shot ahead of the plane. But now that the plane is going at the same speed as those sound waves have nowhere to go. Because they can't go forward, because then the plane's just going to catch up with them again, and then they can't go backwards, because there's a plane there, dummy. So they just shoot off to the side. But they don't shoot off to the side all one at a time. They all compress together into one shockwave. It's like one giant powerful wave that is called a shockwave. And then that just shoots off to the side with incredible power. And then that's what you hear as the sonic boom. It's just bang. It's just a very, very loud boom. So waves in the back, they're all fine. Waves at the front, they are tight together, and they are one giant shockwave. Now this shockwave, let's say the plane is moving this way. The shockwave doesn't just go shoot off to the side. It shoots off at like a pretty steep angle, and so which is why when you're listening, like you see it pass, but then it takes a good set. It takes a bit of time before the sound actually reaches you, and that's because the shockwave is aiming at the back. It's not out to the side. It's aiming it to the back. So that's more or less the Doppler effect, best I can explain it. And then you might be thinking, what is Mach? Like you always hear Mach 1, Mach 2, Mach 3, like all that. It's the speed. It's something Ernst Mach developed in the early 1900s when supersonic flight was coming to the forefront of flight technology. And so it's a way to measure your speed relative to the speed of sound. So he created a formula for it. It's really very simple. So M, sometimes referred to as MA, is going to be your Mach number. V is going to be your velocity, obviously. And then A is going to be the speed of sound. So then what happens, so then the formula is M, or MA, depending on how you write it, is equal to V over A. There you go, that's the formula. So it's the Mach number is equal to your velocity over the speed of sound. Now I say the speed of sound because depending on where you are, speed of sound is different, because if you're at like sea level, it's 770 miles an hour, but if you're at like 20,000 feet, there's a lot less air and it's a lot colder, so then it's it's a lot colder, and so the waves are a bit tighter together, so it decreases the speed because there's less air, and it goes down to like 660 miles an hour about. So that's it really. Sound vibrations in the air, sonic booms are just incredibly loud shock waves that come off when an airplane hits the speed of sound. And then the Mach number is its formula. It's m, or ma, is equal to velocity over speed of sound. Oh, and like Mach numbers, so say Mach 1, that's just 1 times the speed of sound. Mach 2 is 2 times the speed of sound. Mach 3 is 3 times the speed of sound, so on and so forth. That's really just about it, really. That's about everything I can think of, really. Well, let's see. Oh, dear. Is it that time already? Sorry, pal, but I have to go. If you'll excuse me. Toodaloo, and I'll talk to you next time.